So this is the last lecture on antenna array. So in this series of antenna array, this will be the last lecture. Here we will see one more example, one or two more example, then general array design principle, and then some programs. Programs I expect that you will understand the programs, you will discuss among yourselves the programs, and if there is a problem then I will intervene. Otherwise theory part I will discuss, program part you have to discuss. Programs are given in the PDF that I have supplied. Also programs are in this PPT. So you have to discuss those programs, what you understand line by line, so that you will get acquainted with MATLAB programming. So let us start with two-element array, and that we have discussed. We discussed a special class of two-element array when we discussed two-element array. What was that special class? The special class was uniform. Definitely two element means it is linear, but it was uniform. So uniform, now we will consider they may not be, these two elements may not be uniform, which means their amplitude of excitation current that excites the array, which means each element has a different current. Current amplitude is not same, and there is a phase difference, as in the previous case of two-element array special case, there is a phase difference. So if it is not uniform amplitude, then array factor is equal to I0. I0 is the current in the zeroth element plus I1 exponential j psi. Exponential j psi represents the phase part and I1 is the current in the second element. Now let us take I0 common from that. If we take I0 common, so this factor becomes 1 plus I0 upon I1 exponential j psi. So that is the array factor. Now normalized array factor will be this divided by I0. What is normalized array factor? It is the array factor value divided by the maximum of the array factor. So that array factor maximum value will be 1. It will not go greater than 1. It will always be limited to 1. Maximum will be always limited to 1. Therefore, array factor normalized is 1 plus I1 upon I0 exponential j psi. Now, if I1 upon I0, this ratio is equal to 1, then there can be a null. Otherwise, if it is not equal to 1, then there will be no null. Null will be absent. Reason is, it is very simple. Reason is, if the amplitudes are different, as I have told you already, in the far field we are adding the electric vectors. So electric fields are vector quantities. In the far field, the electric field due to the first element and electric field due to the second element are going to be added or subtracted. Now when we are subtracting them, if their amplitudes are different, then there will be a net subtracted value which is not equal to 0. But if their amplitudes are same, two vectors of same amplitude of opposite direction will cancel out and that will give you 0. Then only you will get null, otherwise you will not get null. So this is the condition for getting a null in an array of two elements, that the current amplitude must be same. For both the elements, amplitude of the current must be same. Otherwise you will not get a null. You may get a minima, you will definitely get a minima when the two vectors are subtracted, so you will get a minima, but you will not get a null. So null is absent if I1 upon I0 is not equal to 1. Then I have already told you psi is array angle, so this determines the position of maxima or minima or nulls. In case of equal amplitude, you will get null. So psi determines whether you will get a maxima, where you will get a maxima, where you will get a minima or the null. That is an important property of psi or array angle. Then we will see how to write a program for this. Let me give you a small example for this, then you can discuss other programs. It starts with, I am starting with CLC. CLC means whatever is in the screen, your command window, it has two windows. MATLAB has two windows. One is program window or script window, other is command window. In the command window, whatever you write in the script window remains in the script window. But once you start running the program, each line comes to the command window. Results will come to the command window unless there is a semicolon at the end. If there is a semicolon at the end, it will not come to the command window. Otherwise, everything will come to the command window. So command window becomes clumsy. To remove those clumsiness, we write CLC. CLC means clear the screen or clear the command window. CL is clear, C is command window. So CLC is clear the command window. So that is what I start always. That is a good practice. If you write a program in MATLAB, start with this. Either first line will be CLC or second or third line will be CLC. After CLC, next line is clear all, which means in the memory of the computer, whatever is there, everything will be cleared related to the program that you are writing. So clear all. So next line is clear all. Then close all. So anything that is open like a figure or if you have any other thing, that will be closed, so close all. So this is the sequence that I usually follow. You can follow it in any other way, close all, clear all, CLC, but preferable is CLC, clear all, close all, or clear all, close all, CLC. So whatever is possible on your part, you do that. Then n is equal to 2, n is actually the number of elements, so that is why n is equal to 2. dn is equal to 0.5, that is the separation between the elements. dn is the separation between the elements, that is 0.5 in terms of lambda, so 0.5 lambda. So in terms of wavelength, normalized d in terms of lambda, so dn is equal to 0.5. That is what I am writing. Then r is equal to lin space. Remember this, lin space means linearly space, 0.5 to 1.5 and 5 divisions. So 5 points between 0.5 and 1.5 are linearly spaced on an axis. So r is equal to that. Theta is equal to lin space, again theta 0 to 180 will take. So 0 to 180, there will be 181 points. So that is 181 points. So equispaced, linearly equispaced, 181 points. So that is theta. So then psi is equal to 2 pi dn into cos theta. That expression, you know what is the value of psi. Psi is equal to 2 pi d into cos theta. Now you can see here cos theta, I am writing cos d theta, which means in terms of degree, cos in terms of degree. If you write only cos theta, then it is in terms of radians. So it is cos d theta because I have taken theta in terms of degree, 0 to 180 degree. Now comes your array factor. What is array factor? Array factor is equal to 1 plus r dash. This dash actually shows the transpose of the vector r. R linear space, we have seen 5 elements or 5 numbers. Those 5 numbers are actually represents I1 by I0. So that is for 5 values we are taking 0.5 to 1.5. So that is it. So r dash, then dot star. Dot star means element by element multiplication. So r dash has 5 elements. So each element will be multiplied by exponential j psi. Then array factor normalized is actually absolute array factor. So absolute means you find out what is the absolute value. Then plot. So plot is a plot of 2D. So it is a two-dimensional plot. So plot theta. Theta is defined above. So plot xy gives you plotting of x versus y. So here it is plot theta array factor normalized 1 comma colon, which means colon means normalized array factor of first value. We are getting 5 values now because of r is equal to r has 5 values. So there are 5 values. So first value, then 1 to 180. So that is a colon. If you give colon, it will take all the elements in the array in that. So array factor is a 1 cross 180 element array. So first element of that 1 cross 180 elements. So that divided by maximum of array factor of that add value. So whatever is the maximum value, that will be divided with array factor 1 comma colon. Then r is given within quote, that is the red line. Then so the line that will be plotted is the red line. Then theta array factor 2, theta array factor 3. So similarly, we'll go up to 5 numbers of this. So then red, then after that there is a G that you can see, it is green. Then there are 3 periods, dot dot dot, which means I cannot write this in one line. I am going to the second line. Same program, same is continuing, plot command is continuing in the second line. So that is going like this, then it will continuing in third line. So it will go to the last one. So this gives you the program. It's a simple program for this 2 element array. Now you can see, once I give this command and run it in the MATLAB, you can see 0.5, 0.75, 1, 1.25, 1.5. Now you can remember 0.5 to 1.5 is the range of R, and there are 5 values linearly spaced. You can see 0.5, then add 0.25, add 0.25. So everywhere 0.25 is added. So they are linearly spaced. Now for each of these values, R dash, which means I0 by I1, we have plotted the radiation pattern. So this shows you the radiation pattern, general 2 element array radiation pattern you see. Now let us come back to binomial array. After this introduction to 2 element array, let me come back to binomial array. This we have already discussed, that binomial array, in case of binomial array, the coefficients of the current amplitude are binomial coefficients of a polynomial. So that is what we are showing here, 1 to 1. So it is a polynomial of 3 elements are there, 1 to 1. Spacing is delta. So between 1 and 2 spacing is delta, between 2 and 3 spacing is delta. Current amplitude is 1 to 1, middle one is amplitude is 2, otherwise it is 1. So this you get from binomial array or binomial coefficient expansion. We have discussed it in the last time. So last 2 will be always 1, then in between will be add them together, that gives you 2. If there are 3, then 1 3 3 1, 4 1 3 6 3 1. So that way it will continue Pascal's triangle that we have discussed already. Binomial array, you know the speciality of this is there will be no side lobe. So if you have a binomial array, there will be no side lobe, and the current amplitudes are binomial in nature, binomial coefficient. Example we are seeing here again, the same example, 1 to 1. So for this z is equal to -1, that you can write as e to the power or exponential j psi. Z is equal to -1, you take z is equal to -1, or z plus 1 is equal to 0, that is the polynomial. That polynomial we are considering. So array factor is mod of z plus 1. Now that will show you null is at psi is equal to pi. So if null is at psi is equal to pi, and array factor is now you can write z plus 1 to the power n, which means there will be n number of repeated loops, repeated zeros. Everything for 0, each 0 is 1. You can take n 1, 2, 3, 4, anything. Always 0 will appear at the same point. Z is equal to 1 or psi is equal to pi. There you will get the null. So n nulls will be repeated at psi is equal to pi, which means there will be a narrower bandwidth. So using binomial array we will get a narrower bandwidth. This example is we are taking n is equal to 2. If I take n is equal to 2, z plus 1 square, n is equal to 2, so z plus 1 to the power n is z plus 1 square, which is 1 plus 2z plus z square. So array factor is z plus 1 into z plus 1, absolute of course. Then now for delta is equal to lambda by 2, which we are considering throughout our discussion. So if I consider delta is equal to lambda by 2, this array 1, 2, 1, this I can consider as two arrays of 1, 1, then another array of 1, 1. So there are two arrays, 1, 1 separated by lambda by 2, then another 1, 1 separated by lambda by 2. So since there are two ones, they will add up to give you amplitude 2. So that you can see. So this is how we represented that. So three elements that we consider as four elements, each of amplitude 1. So now the top one you can take it as a binomial array, simple array of amplitude 1, 1. Second is also amplitude 1, 1, same amplitude. So it becomes uniform array. Once it becomes uniform array, you can find out what is its pattern. So for the first one, the pattern will be figure of 8, which will be exactly as if there is a one point, one source which is exactly between these two elements. Therefore that point will be at the center. So from that point, each of these elements will be delta by 2 separated. If they are delta by 2 separated, similarly for the second one they will be delta by 2 separated. So the two equivalent sources will be delta separation, because for the first one it is delta by 2, for the second one it is delta by 2. The center one is at delta by 2 from the first equivalent source. The center point is again delta by 2 from the second equivalent source. So the distance between the two equivalent sources is delta, and each equivalent source has a pattern of figure of 8. So when we have delta is equal to lambda by 2, this is what we are getting. So pattern of figure of 8, that we know how it is represented. So array factor 1, AF1 is the array factor for any two of those elements that I showed. So that is cos pi by 2 cos theta, that we have already seen, so I am not going to discuss it anymore. So this is the primary pattern. This is called the primary pattern of the array factor, PP, or primary pattern of the array factor. Then since now we have two elements whose primary pattern is AF1, there ultimately you will get the array as the primary pattern into array factor. So again array factor is, they are separated by delta, which is lambda by 2. Again, if two elements are separated by lambda by 2, then the array factor for those two elements is same, cos pi by 2 cos theta. So put that cos pi by 2 cos theta. So net array factor is, total array factor will be cos pi by 2 cos theta into cos pi by 2 cos theta. So that gives you the array factor for the binomial array, if I am considering three elements, 1 and 2z plus g square. So now this part I am going to leave out. You can easily write the program CLC, clear all, close all. N is equal to input number of elements, which means the computer will ask you to input number of elements. Whatever you input, that will be taken by the computer as capital N. Then 1 to n minus 1 is equal to 1. So everything is taken as 1. Number, each element 1 to n minus 1 means you have n minus 1 elements. You are taking them as 1 to 1. Then theta is equal to, as in the previous case, 0 to 180, 181 points equally spaced between 0 to 180. So that is theta, and that is why linearly spaced. And then dn is equal to 0.5, that remains as it is. Psi, we have already seen how to write psi, so that goes there. Then for k is equal to 1 to length of L, L is equal to whatever will be L, length of L plus 1. So then that gives me total number of elements, because L is equal to 1 to n minus 1, that I have taken. Total number is n, n minus 1 elements we have taken, that is why length L plus 1. So k is equal to 1 to n, now it becomes k is equal to 1 to n. Now find out what is the Lk. So each Lk we are going to find out. N choose k, length 1, k minus 1. So that is, this is actually n choose k is actually the binomial coefficient. So that is how you are finding out the binomial coefficient. Each binomial coefficient I have found out, that I will be using. So there you end. Then give the fetch. Percentage sign means it is a comment line, so that will not be evaluated by the computer. Then pH, so is fetch. So fetch is 0 to 1, and that will be divided by length L minus 1. Length L is n minus 1 points between 0 to 1. So now find out what is phase. It is j phi into psi, that we know. Then go for exponential. So exponential is exponential of phase, that I write. Then find out what is RA factor. You know the formula. It is sum of the exponential, all the exponential. I am going to sum it up. Exponential, whatever is the exponential value, into ideas. What is ideas? Ideas is transpose of I, so that dot star of exponential. So that is 1 plus e to the power j psi plus e to the power 2 j psi. That is that sum is written by this method. So sum means sum of all those terms. Then array factor normalized will be array factor by maximum of array factor. So whatever is the maximum value in the previous line, that will be calculated automatically, and that will be divided by the array factor. That gives you the normalized array factor. So once you know what is the normalized array factor, you can find out what is the AF1. So find out what is AF1 using this, sin n psi by 2 divided by n sin psi by 2. So that is the formula for array factor. So for of n elements, so that we know. We are using here array factor 91 is equal to 1. I am taking. The reason is very simple. At the point 91 array factor, we are in the above line, it will calculate array factor at all points, all the 180 points. Now out of that, at the 91st point, it is 0. Psi is equal to 0. So sin 0 divided by sin 0 for. So that is not calculatable. You cannot calculate. You will get a NaN, not a number, or infinite. So to avoid that, what I do is, as you know, sin x by x is approximately 1 when you go to when x goes to 0. When x approaches 0, sin x by x is equal to 1. Therefore, for that particular point, AF1 91 is equal to 1. So that is the point where theta is equal to 0. So for that point, we are making AF1 is equal to 1. So then we go to plot. Then you plot it binomial array. Then hold on means hold the plot on. So that will be, it will not be deleted. So it will remain as it is. Then you can plot anything above that. So one plot, if I want a second plot, the second plot can come after hold on. If I don't write hold on, then the first plot will be deleted and second plot will come. So therefore we put hold on. So then you write the hold on. Finally, once it is over, put hold off. So that is what it is. So you can see uniform linear array versus binomial linear array. Binomial linear array is green, uniform linear array is blue. You can see binomial has the no zero, no side lobe, nothing is there, but its beam width is wider compared to the uniform linear array. On the other hand, the uniform linear array has side lobes, it has zeros, so those things are there. They have their advantages and disadvantages, which we have already discussed. Practically, people do not use binomial array because directivity is degraded there. Then come to a linear array. So we'll consider now the linear array, design of a linear array. 2n plus 1 symmetric elements we will consider, so total number of elements is 2n plus 1, which is odd number. So in that case, array factor will be I0 plus I1 e to the power j psi, or plus ultimately I2n exponential 2n j psi. Now because of symmetry, what we can do is we can write this in this manner: I minus 1 exponential minus j psi plus up to I minus n exponential minus n upon psi plus I0. So I0 is the center term or the center element. With respect to the center element, towards the left phases are decreasing, towards the right phase will increase. Therefore center element is I0. Go up to I minus 1 in the left side, go up to In on the right side, or you can write that as I minus n to I minus 1 on the left side, then I1 to In on the right side. Center is I0. So that is the array factor. The moment to write that array factor, I can write that as a sum. So array factor is sum of k is equal to minus n to n ik exponential jk psi. That is quite easy to remember. You can write now, if you look at this, then I can write ik is equal to minus, ik is equal to ik minus star. Ik minus star means star is complex conjugate of ik. So ik is equal to ik minus star, or I minus k star. That gives you the complex conjugate. That we can write as ik amplitude exponential j alpha, which you can also write because ik is a complex number. So since ik is a complex number, I take the real value or amplitude as ik mod exponential j psi. That you can write as amplitude of ik cos alpha plus j amplitude of ik sin alpha using Euler's formula, Euler's identity. So that I can write as it's a complex number, so I can write it as pk minus jqk, where pk is equal to ik cos alpha and qk is equal to ik sin alpha. So once I know that, then I can write I minus k is equal to pk plus jqk, because I minus k star is equal to ik, or I minus k conjugate is ik, or ik conjugate is I minus k. So I minus k, ik conjugate is pk plus jqk, write that way. So I minus k is pk plus jqk. Now let us let us see how to simplify this. Now take any two terms, two conjugate terms, ik exponential jk psi plus I minus k exponential minus jk psi. So k can be anything from minus n to 1. I0 remains as it is, it cannot be 0, because if you take 0, then it is exponential j 0, so that becomes 1. So it makes no point. So ik exponential jk psi plus I minus k exponential jk psi. So for ik I can write pk minus jqk, and then exponential jk psi is cos k psi plus j sin k psi. Similarly for the other one, pk plus jqk, then cos k psi minus jk j sin k psi. Then if I do a simple algebraic addition, multiplication and addition, exponential, sorry, the imaginary part will cancel out. I will be left with a real number. So that real number will be 2 times pk cos k psi plus qk sin k psi. So ik exponential j k psi plus I minus k exponential minus j k psi is equal to 2 times pk cos k psi plus qk sin k psi. Now the moment I write this in this form, then you can easily remember the Fourier series expansion. So let us go to the design using this. We have found out this array factor is equal to summation k is equal to minus n to n ik exponential j k psi, that is 1. Then by expanding that, we have also seen array factor is equal to summation k is equal to 0 to n pk cos k psi plus summation k is equal to 1 to n qk sin k psi. Now this is the power series. If you remember, this is the power series, which also is called a Fourier series. So this is the Fourier series. Both these, the top one is the exponential representation of Fourier series, bottom one is the sine cosine representation of the Fourier series. So array factor can be written as a Fourier series. So that is what we have seen now. Now if I write the array factor as a Fourier series, for design of the array, what I have to do is I have to find out what is ik or what is pk and qk. Once I know those values, those are the amplitudes of the excitation, current excitation. So my array factor term is done. So let us see a design example. Let us try to illuminate a sector of 60 degree. So there is a beam which is illuminating a footprint of 60 degree in broadside and 0 elsewhere. There are only 5 elements. So this is the given data to you. The number of elements is 5, beam width is 60 degree, and beyond the beam width there is nothing, everything is 0. So only I have to generate a beam of 60 degree, so which has a beam width 60 degree, beyond that everything is 0. So that much I want to illuminate. I will use this general linear array design for that. So for the solution, number of elements is 5. Theta is between minus 30 to 30. So minus 30 degree less than theta less than 30. For full coverage of the visible region space, we are taking delta is equal to lambda by 2. देखे कि एंट्री की করছি কি So for full coverage of the visible space, delta will be equal to lambda by 2. If delta is less than lambda by 2, then we will not get the full coverage of minus 30 to 30. If it is greater than that, then we will get, there is a possibility of getting lobes. So considering this, my array factor will be 1 when minus pi by 2 is less than psi is less than pi by 2, and it will be 0 elsewhere. This is given to me. Now array factor is symmetric. It is between minus pi by 2 to pi by 2 or minus 30 to 30. Total is 60. Array factor is symmetric. Therefore, it is an even function. Since it is symmetric, it is an even function. The moment I know it is the even function, then Fourier series, all sign terms will drop out. All qk will be equal to 0. So all qk will be 0 and ik will be 1 upon 2 pi integration from minus pi by 2 to pi by 2 exponential minus jk psi d psi. So integrate that. It is simple integration. Put the limits. That will give you minus 1 upon jk pi into minus j sin k pi by 2. Qk will be 0 because all sign terms has to be 0 for an even function. Then P0 will be 1 upon 2 pi integration minus pi to pi d psi. So that will give us 1 by 2. Then Pk, simply integrate it 1 by 2 pi minus pi by 2 to pi by 2 cos k psi d psi. That will give us 1 by k psi sin k psi k pi by 2. So that is, so I have got everything. My Ik is equal to P0 or Pk, etc. Now the question is, you design the array or write a program for your design to test whether it is going properly or not. So this is the program CLC clear all. P0 is equal to 0.5 that we have found out. Then P0, this you have to explain now. I am not going to tell this among you or yourself. You have to discuss and come out with what is this. P is equal to 1 upon pi, which means this one shows P has 3 elements. 1 upon pi, 0, minus 1 upon 3 pi. So that is what P is equal to, that within square bracket. And that shows 3 elements. 4 elements you can add another element. And these are all in a row, single row. If they are separated by comma or space, it is row. If they are separated by semicolon, then it is column. So that is P. Then you define theta as earlier. So then you have to implement what we have done. So dn will be this, psi will be this. All these things I have already told you, so I am not going to discuss it anymore. K is equal to 1 to 3. K psi is equal to K transpose into psi. Now element by element multiplication, array factor will be this. Cos d, you know, it is finding out the degree, evaluating cos in degree. Then you normalize that, normalize the array factor. Then find out what is theta 1. Theta 1 will be a cos d, which means inverse of cos d. So find out what is the theta 1. Plot theta 1 versus array factor normalized. Limit this x limit I am putting on the x limit minus 182, 0 to 180. So that is, beyond that it is already 0. I know that it is going to be 0 beyond that. So that is not of any interest to me. Theta is equal to 0 to 180 is of interest to me. Now you can see that this plot gives you a 60 degree beam. And so the design is correct. So with this, effectively we complete everything on array, including generalized design, other designs. Now if you want to see Dov-Chebyshev design problem, please go to the last line. Last line shows you a YouTube channel where you can see the Dov-Chebyshev design problem. It explains very nicely, step by step. It explains how to design a Dov-Chebyshev design problem. The design problem is given here. This is, you can note this link and go to the YouTube and see that link. Finally, I will come to the gating loops once more that we have discussed. Actually, gating loops are spectral images. It is equivalent to spectral image as in case of your communication or signal systems, DSP, etc., where you look at spectral images. Here we look at gating loops. So they are equivalent. Their generation is because of the sampling of the space. Like spectral images are generated by sampling in frequency, here it is sampled in space. In the site in space, these images fall within the Nyquist interval other than the central one. So if the central one is only within the Nyquist interval, then you get one loop. If there are other images, the other spectral images are coming to the Nyquist interval, then you get more than one loop or one loop, which are called the gating loops. Now how to find the number of grating lobes? It's very simple. Find the number of complete Nyquist intervals fitting within the width of the visible region. That we have already seen. So m is equal to psi visible upon 2 pi, that is equal to kd by pi, which is 2d by lambda. That you know, that from that you can find out how many grating lobes will be there. To avoid grating lobes, what you have to do? Make kd less than equal to less than 2 pi or d less than lambda. So that will ensure that your grating lobes are not there. But this condition does not necessarily avoid aliasing. Aliasing can be there. This condition only avoids the grating lobe. So aliasing can always be there. You know what is aliasing? Aliasing means you do not recover the signal in the exact form. Similarly, you do not. This ensures that this will not ensure that you throw the light or your radiation pattern is what you exactly wanted. So that may not be the case, but there will be no grating lobe. So that is there. If d is in the range lambda by 2 to lambda, or pi is the or kd is in the range pi to 2 pi, then you are avoiding grating lobes. But this is part of the Nyquist interval repetition. Now for complete removal of repetition, d has to be less than lambda by 2. But I will tell you something else. As I told you already, that we get no grating lobes in the broadside. There are two total space we can divide into or put it in the range broadside to end fire. Right? If it is in the broadside, there will be no grating lobe if d by lambda is equal to 1 or d is less than equal to lambda. And if it is in the end fire direction, then d is less than equal to lambda by 2. So this is the range. So d by lambda has to be within 1 and 1 by 2. It cannot be more than that. So for that there is a cute formula. You do not require to derive that. You can simply write or remember, this is a very simple formula. D upon lambda is less than equal to 1 upon 1 plus absolute of sin theta. Now what does that mean? If sin theta is equal to 0, then that is 1 upon 1 plus 0, which is d by lambda is less than equal to 1. That is for the broadside. Theta is equal to 0 is for broadside. So that gives you for broadside. Now if theta is equal to pi by 2, then sin theta pi by 2 gives you how much? 1. So 1 by 1 plus 1, which is 1 by 2. So d is less than equal to lambda by 2. So if it is between these two, 0 to pi by 2, put that value and you can find out that okay, if I am going to aim my main beam in this direction, in this particular theta direction, then my d by lambda should be this. That you can find out using this equation in your design. Then you can write the equation for grating lobes in the form of a program. This is the program. I am not going to explain this program anymore. That you have to do. Plots, subplots, etc. So programs you will discuss among yourself. I think that is that's all that I wanted to discuss. Grating lobe illumination. Okay, then finally I will come to this array failure, which means you take an array of 5 elements, 10 elements, 20 elements. If one of the element has failed, it's not working properly, what will be the pattern, how much it is going to change? That you can see. For that you can write a program, a small program, and see what happens in case of failure, array failure. Once array element failure, one element fails, or a phase shifter fails, which is giving the phase to the array element. If that happens, what is going to happen? So this is a program for array failure. You can see what happens in case of this array failure. Now I think I will stop here. I will leave it to you, to all of you. You can see what has happened in array failure, what is happening. I will like you to explain what all those figures, how those figures have been obtained, explain the program. So one of you can share the PDF that I have already given in the Google Classroom. So one of you can share that, then keep on discussing about the program. If you do not understand any line, what is happening there among yourself, you do not understand, then I will intervene and I will clarify that. I want you to understand those things on yourself.